So let's look a little bit into adhesion and what makes things stick. Now, we've seen part of the adhesion in the resin cements, but basically we want a good combination between this and a very, very old product, the glass ionomer cement. Glass ionomer cements, in a way, are the first self-adhesive products. They can stick to tooth structure, but they are mechanically not very strong and they don't look as good as resin cements. Now, tooth structure is one thing, the substrates are the other thing. So what can we do about noble gold alloys? And the astonishing thing is we can bond to these. We can bond to these via sandblasting and putting a special primer on them. It gets more difficult though when we get to a regular non-precious metal substructure. There's nothing we can do. There's pure friction only that we can use to hold these in place. What about the full ceramic restorations? Now, basically that depends. Cyanidization is good for glass ceramics, but it does not work on these high-strength ceramics like zirconium dioxide or aluminum oxide. So what are these? And what about the substructure of the tooth? What we find is that, like in a bonding process, enamel is said to be more reliable and easier to bond to, and dentin more difficult. And consequently, there's products that work very well with enamel, and there's products that work well with dentin, but there's very few products, and we are really proud to say this, that work with both of them, like Permacem 2.0. So Permacem 2.0 is really an exception of the rule, and bonding to tooth structure is good. But how do we achieve it? So if you look at this picture, you see that this is one of the special bonding monomers that we use. And it's basically grouped in three parts. Part one, if you compare this to the phosphoric acid down below there, so if I overlay this, you will see, it is basically a modified phosphoric acid. And then we have this long chain that can interact with the surface. If it's done right, it can give you adhesion on specific surfaces. And the last part finally has this double bond which allows it to be incorporated into the curing resin matrix of the cement. So that is that. And naturally, this structure, if done right, can also adhere to zirconia. This is one of the big features of Permacem 2.0, to get you a very, very good adhesion to zirconia. And in order to allow you a little bit of insight into ceramics, let me classify these into basically into three groups. So there's aesthetic ceramics, and these aesthetic ceramics have a high glass content. The usual thing is feldspathic or lucite reinforced ceramics. The next group is the structural ones, and these have a lower glass content, and lithium disilicate is the thing here. So lithium disilicate, which is also called Emax, this is a trade name, is the really, really big newcomer on the block. And last but not least, we have high strength with no glass, and this is zirconium dioxide or aluminum dioxide. And these materials need special bonding agents or cements, basically. So high glass needs bonding and needs a resin cement. Structural can be done with a self-adhesive cement, and a high strength can use and should be used with self-adhesive cements or resin cements, but can be used even with a phosphate cement. And to do this, we need one more component in a self-adhesive cement, and that is water. And in this, you can see a bit of the differences between scientific and marketing ideas. So as a scientist, I say we need water to make the product react. The acid group needs it. And the marketing department says, so it needs water, so then we can say it's water tolerant. But let me show what I mean with it needs water. You would probably call this pop rocks. So this is a German thing like it. And as long as it's in this bag, nothing happens. But if I pour it here in a glass of water, it starts to bubble and foam and go off. So at once the acid gets this water contact, then it starts to react. And this is what we want with Permacem 2.0. We want that certain moisture content, no water puddles, not like this, but we want a moist surface to react. And we don't want eugenol because it's a resin cement. Any resin cement doesn't want eugenol because it can inhibit the polymerization. And with that, I'd like to show you a little bit of what Permacem can do in the next part. Thank you.